Hello, I'm Kevin Pouget. I'm a senior software engineer in the Red Hat Spice team, and I'm going to talk about the work we've been doing in the adaptive streaming project. So the idea of adaptive streaming is that the video streaming will use resources. It will use the CPU and the GPU on the guest. It will use network bandwidth to transmit from the host to the client, and it will use CPU and GPU on the client to decode and display the video. But these resources may change over the time. The user may run CPU or GPU intensive workloads either in the guest or in the client side in his laptop. And of course, the network might get congestion over the time for different reasons. So what we want to do with Spice is to adapt in real time the streaming parameters, the streaming quality, to the available resources for an optimal usage. Now let me introduce the recording infrastructure, the infrastructure that allows us to monitor the state of the different systems. First of all, we need to have Spice running in each of the systems. On each of these systems, we deploy a local agent in Python that will be in charge of collecting the different events, the different statuses. In this local agent, we will run multiple plugins that will monitor different aspects of the system. For instance, the CPU load, the system RAM load, the state of the GPU, and indication specific to the Spice process, so in particular how much CPU it's consuming. And last, and not the least, the Spice indicators, which are Spice internal information, such as the encoding and decoding time, the size of individual frames. And all of these agents, all of these plugins, they will run identically in the three systems. And for the research phase, we will collect in the performance collector all the indicators, either for a live view or for offline processing. So now let me connect the recording infrastructure to Spice components. I don't need the desktop. I connect one agent to QEMU, one to the client, and one to the streaming agent. And now I can launch the performance collector. And the performance collector will connect to the three agents, receive the table they are able to share, and based on the streaming, the data generated by the streaming, everything will be gathered by the performance collector here. Now we can switch to the web browser and have a look at the control interface. So in this panel, we can control which codec is currently used, which codec is we want to enable. So if we switch to Intel VP8 encoder for JStreamer, we see that we have different parameters that we can control. And the performance data, they are collected in real time by this tool. So we can see the load, the system load of the different systems, Same for the GPU in the guest, server, and client. And here it's the CPU usage of Spice streaming agent in the guest, QEMU and Spice server in the server, and Spice GTK in the client. So one information that we can study is the frame size. So here in blue we see that most of the frames are very small and a few of them are between 400 and 500 kilos. We see that there is a wave pattern. This is because of the train going from one side of the screen, sometimes being out of the screen. And these big frames that we see, that's what is called keyframes in video encoding. So if we, for instance, change the keyframe period, we put something like 246 and we go for it. Then we go back to the size and we see that there is no more keyframe for a while, one keyframe. The encoding parameters we want to study, it will be, for instance, the bit rate, how much data should be transmitted over the network, the frame rate, how many frames each second, the resolution of the screen, and maybe the keyframe period, how many full frames should be transmitted every 1 second. And we want to study the impact of these parameters over multiple resources. The GPU, CPU consumption on the different system, the size of the frames, the frame rate we're able to deliver, etc. And we want to see this impact over multiple use cases of the VM for office work, for 3D processing, with a still desktop. And we want all of this study with different usage of the resources. One CPU is busy, one GPU is busy, the network is getting slow. So if we sum up all the combination of these different parameters, the number of experiments to run gets really high. So the conclusion is that we need to script all of it to be able to run it and reproduce it easily. Let me quickly introduce how the scripting engine is working. So in this configuration file, we define how the benchmark will run. So at the beginning, we specify some parameters for the different display use cases. And then we say what experiment we want to run. So all of those are disabled. And the one I'm currently running is a study of the FPS parameter, the frame rate, for Intel H965 media driver. So when I will run the experiment, we will set the Intel VP8 encoder, and for the encoding parameter, the frame rate will take the value 20, 25, 30, etc. The bit rate will take these three different values. The keyframe period won't change, it will be the same for all the benchmarks. Same for the rate control. And two different displays will run. One WebGL dynamic, one static image, for two different resolutions. And the recording time will be 40 seconds. So this first set of parameters, they configure the encoding itself. And the second set of parameters, the script, it's for the environment. So at the bottom of this file, we define how we want to change the display, how we want to change the resolution. So for instance, for the resolution, we will execute the VM script that will change with X around R the resolution. And once we've finished, we will set back the normal resolution. Same for changing the display. The VM script will launch Firefox inside the virtual machine with the given URL as parameter. So if I run the benchmark in dry run mode, we see that 96 experiments have been prepared, and it would have taken 85 minutes. Now, if we look at the very last one, for instance, here we have the encoding parameters that were configured. So the still image, 40 seconds, the 1K resolution, and frame rate 120. Then we reset the state of the encoder, we set the current parameters, wait 10 seconds for everything to stabilize, clear the performance collector internal state. We record in the performance collector, we record the parameters of the benchmark so that we can access them later on. Same for the encoding and decoding pipeline. We ask the agent and the client to share it with the performance collector so that later on we can study the pipeline and understand if one thing was wrongly configured or if everything was correctly configured. And we wait 40 seconds to have enough data for processing. And we save it into a file. And then, as this was the last record, we shut down everything. We set back the default display, default resolution, and we turn off the performance optimization, etc. And to actually run the benchmark, I just change the command line and add run, and this will actually do the configuration of the systems, launch Firefox with the WebGL demo. So here it is. I'm waiting for a few seconds, clear everything, and now that's recording. And this benchmark will go for more or less 85 minutes. Now let's have a look at the results of these benchmarks. So we can start loading, still with the FPS study, we can start loading the guest CPU usage. So in this graph we see all the experiments that have been executed. So that's many results. Here, this side of the graph is for the static image. The other side is the WebGL1, the dynamic display. And for the 4 different parts of the line, this first one is 720 resolution, and this part is 1080 resolution. And same for the dynamic display, 720 here, 1080 there. So quickly we see that the static image will use less CPU than the dynamic one. Now we can have different looks on these results. So for instance, here we have 2 resolution, 2 display. So we can say that we don't care about the 720 part. We only want the 1080 resolution. So in the menu, I select 1080 resolution, and now we compare the static image with the dynamic WebGL screen. Our final goal is to be able to model the behavior of the resources when the different parameters change. So we started doing some modelization with at first some regressions, linear regression between, for instance, the guest CPU and the frame rate. So we see that for each bitrate setting, the CPU usage is quite linear compared to the frame rate. Once we've been able to find different relations between the resources and the settings, we could merge them together and have more dimensions in the modelization. So currently we've got it for the CPU and GPU. For the CPU, when we study the frame rate, the resolution, and how it influences the guest CPU, we see this 3D model. So here we've got between -1 and 2% of error, which is quite good. And if we add multiple resolutions and multiple display, for the display, it won't be the same parameters that will be used. So we have 2 plans in the model. One for the static image, one for the dynamic screen, that we can see clearly when we move the 3D representation. So here we've got 84 measurements with 3% of distance of error for this modelization. We've got something similar for the render engine of the GPU, with some more error in the current state. We can see in the graph the error level based on the different colors. When it's green, it's very low. When it's red, it's farther. So this point is 11% of error. Thanks for watching. If you have any question about the project or the code, how to adapt it to your environment, feel free to get in touch. Thank you, bye bye.